Welcome to Study Loop.
In order to find the impedance of the circuit, we use equation 21.15 without a capacitive reactance. So Z will be equal to root over of square of resistance plus square of inductive reactance. So XL square. And here we don't have any capacitor, so there is no involvement of capacitive reactance in Z. So Z is the impedance. Now, in order to substitute for XL, that is the inductive reactance, we use equation 21.11b. So that gives the reactance of the inductor here, and that is equal to 2 pi times frequency times inductance square of that. And let me just write down the values that we are given. So the resistance is given to be 36 times 10 to the power 3 ohms, and inductance is 55 times 10 to the power minus 3 Henry. And the frequency F is different for both the parts of the problem. So for part A, frequency is 50 Hertz. So we substitute these three values in this equation. Let's call this equation 1, and let me keep it inside a box. So we substitute these three values in equation 1, solve for Z, and we find Z to be 3.6 times 10 to the power 4 ohms. And basically, the inductor has essentially no effect on the impedance at this relatively low frequency. That's why Z comes out to be very close to R. So in real, Z is actually, let me just write the exact value. So Z is 3.609 times 10 to the power 4 ohms. So you see Z and R are almost equal. And this means that the second term over here has no contribution, and that is because of the low frequency. Now for part B, let me just go to the next page. So for part B, R and L stay the same. The frequency is changed, and here frequency is 3 times 10 to the power 4 Hertz. So again, we solve this equation with the new frequency and find impedance to be 3.7463 times 10 to the power 4 ohms. So now if you compare Z with R, you'll see that it is quite large, which means that the second part of the equation has a impact on Z, has a contribution, and that is because of the high value of frequency. Thank you.